Okay, so we're going to talk about the homework 2.3 that's due today. Hold on to it. For now, we're going to go over here in class. Be sure to hand it in at the end of class on your way out. But you can make corrections to your homework while we're discussing it. No class Friday, as I've mentioned before. On Monday, homework 2.4 is due, and you have some reading from the text associated with that, pages 40 through 44. These next two reading assignments, this one 40 through 44, I want you to read very carefully. He really lays out something very fundamental having to do with vector calculus and the understanding of vector calculus. So read it very carefully. He chooses his words, as always, very carefully. In fact, this text, we've been through this before. This textbook you need to read very carefully always, but especially this part, pay close attention, and the next reading for Wednesday of next week will be the next 5 pages or something like that. We're going to get into the divergence theorem and Gauss's law and Gauss's theorem and stuff. Pay very careful attention to what he's explaining in the text, because it will really make the rest of the semester a lot more understandable, a lot more intelligible. Okay, so let's see, before I go on to with the homework, I'm going to, let's see here, turn on this hello? No one turn that, okay, there we go. Now, I'll turn this on. That should show up, there we go. Okay, give the camera a moment to adjust. Okay, so this cell has some fluid in it with little particles and 2 electrodes here. And I have already charged it up by use of this handheld electrostatic generator. And the result is there's an electric field then. The 2 poles, these are 2 oppositely charged poles, so this is a dipole field. What you're seeing here, the particles in the fluid line up parallel to the field. Now we'll study that later, why it is that electric dipoles and magnetic dipoles line up the way they do in relation to the field. So you can see the direction of the electric field here. And now this is the near field part, right? It's the part in close to the dipole. So it's the field in between the 2 charged bodies forming the dipole. And we studied in the homework that we're going to go over today the far field. To study the far field in this case, I would have to bring these 2 close together, and then I'd have a much bigger cell, and then I could study the far field. And as we studied, we'll study in the solution the far field, when they have oppositely charged poles like that, the far field falls off very quickly, so it gets very weak. But in between the fields here, in between the dipole, the charged bodies forming the dipole, the electric field lines look like that. If you get in close, so study this, if you get in close to one of the charged bodies, the field emanates radially outward, just as you would expect. So if you get really close to just one of the bodies, it looks like an ordinary monopole field. And up here it does the same, but these are oppositely charged, and in fact you could follow these lines here going from one end to the other, right, in the sense that the electric field is emanating outward from the positively charged pole and inward from the negatively charged pole, so you can see the structure of the dipole field from that. Okay, so now these are kind of oily, and I have to be careful. This liquid in here is kind of messy. I don't want to get oil all over myself or all over the generator. Here's another one that's interesting. So this is a parallel plate. So we've got 2 plates, 2 flat metal bodies, metallic bodies, and so it's like a dipole in a sense, except that the bodies have been extended, and we're going to study again the near field in between the plates and demonstrate what that looks like by charging it up. That's pretty good. Oh. Okay, and again, what we're looking at here is the field in between, and of course, you see all kinds of interesting things going on. One is you can see in between the plates here, the field lines, the electric field is looking pretty uniform. Because the lines are parallel to each other, and the strength of the electric field looks like it might be more or less the same direction and strength. And then when we get outside here to the edges, we get what are called fringing fields. Getting outside of the region in between, it would be nice to have a parallel plate like this where the plates are extended farther. So you can get, what we're going to examine is, when we study this coming up, the electric field in between these parallel plates where you're far from the ends. So you make these plates extend them way out. Then in that case, we'll find that the electric field in that region between the plates when we're far from the ends is very uniform. So you can generate a very uniform electric field over an extended region by taking parallel plates, charging them up, and as long as you stay away from the edges, you have a nice uniform electric field that you could do experiments with, for example. Okay, now that's the near field. Far field, what would this look like?
Fall off very quickly.
It's going to be another dipole field, isn't it? Right. Get far away, the distribution, the details of the distribution of the charges washes out. You get less sensitive to the actual structure, how the charged bodies are arranged. Get far away, it's just going to look dominantly like a dipole field again. Won't look very different than the previous one, far field. And it will fall off quickly. Okay. Here's one more. This one kind of touches on something we'll come back to again, but it's kind of here, so I'm going to demonstrate. I'm going to go ahead and use it. Let's try charging this one up. A little different geometry. I don't see anything yet.
Tiny little bit.
There it goes, a little bit there. In between the two, right? So the inner circle is charged one way, and the square outside is charged opposite. And okay, aside from being not quite uniform field, one thing to note is that no matter, even if I continue to charge this, there are no fields inside. There's no electric field inside that inner. And we'll discuss that as we come to it later. So even though you could get quite intense electric field in between, there's no electric field in the middle, in the interior. Okay. I think I can just put this down. And then move back over here. Okay. Was that showing up? I hope that was showing up on the camera. I hope that was. Yeah, I don't know. Was it showing up on the camera? You checked back there?
A little small one?
Yes, sir.
Yeah.
Okay, good. Thank you. I just realized I might not have had the right button. I'll have to do it again after class if that's the case. Okay, so let's go briefly over the homework. You've got the solutions here. I just want to discuss any questions that you might have at this time. So we have the first field is x hat plus y hat. The strength of that field, the magnitude of it, goes like the distance from the origin. And so these vectors point radially outward. In fact, you could say that this is in fact r hat, right? Or just r. Yeah. And so these should, in your sketch, you should get a sense that these vectors are pointing outward and increasing in strength as you get farther away, like this. Okay, that's basically what I'm looking for. A little bit more than this. The solutions, the drawings in the solution are a little bit more than I expect from you, a lot more detail. But I wanted to make sure you had a clear idea of what they look like. but a sketch, when I ask for a sketch, might look like that. Okay. So the second one is yx hat minus xy hat. And that is one that looks like a vortex. Again, the strength of that is just exactly the same. It increases linearly in proportion to the distance from the origin. So, and as you get close to the origin, the magnitude of that field, the field lines, the field vectors, decreases to 0. So it should look like that. And then you're playing with some other ones that are related, just to get a feel for how the vector fields depend on distance. So this one is the next one, over x squared plus y squared. So the magnitude of this goes like 1 over r. But it's nonetheless directed radially from the origin. So it looks a little bit like a previous one, except that it's going to get bigger as you get close to the origin. And of course, in drawing this one, you have a problem. You have to exclude some region around the origin. So you might want to indicate here, I'm not going to draw any vectors inside of that region because it gets really big, and it's impossible really to make a nice sketch of it in this way. But the vectors get weaker get shorter, have less magnitude as you get farther out. Okay, and then a similar one. Okay, so this one was a little bit different. X hat minus y hat. Just change the sign on the y component, and that gets you into this one that flows inward like this. Flows inward along the y-axis, outward along the x-axis. Looks like this. So I hope that when you were making these drawings that you kind of started imagining these things as related to some kind of motion, some kind of fluid flow. Something is flowing in this kind of direction, in this kind of fashion. Is it possible, and asking yourself, is it possible, for example, for water to do this? Is there a way that you could do something in your sink or bathtub or kitchen or something where you could get fluid to flow in this fashion? So I hope that kind of naturally suggests itself to you, that question. Okay, and then the last one was, another one was yx hat minus xy hat, like the previous one, the one that was like a vortex. Again, the magnitude here goes like 1 over r now, diminishing. And so it's got that kind of vortex flow, but it's now getting very large near the origin, so you want to exclude some region from drawing. And then you look at this and you can see that the magnitude is diminishing as you get farther away. Okay, so it's the direction and magnitude of these fields are what I'm trying to help you to learn how to sketch and visualize for yourself in your imagination. And then also here's one that's just like a previous one but shifted over, so you recognize when you can just shift the origin of the coordinate system, you may have a field that flows around or it emanates from a different origin. Okay? Any questions about those sketches, things like that? Okay. And now we're looking at general electric field. So once again, if we have a charge Q at a position r prime, which are Cartesian components, x prime, y prime, z prime. And we also have then, we want to know the electric field at a position r. Then the electric field is given in term, and the Cartesian components here are x, y, z, of course. Then as we've written down before, the electric field in Cartesian form looks like this. And this is useful for calculating things. But the content is the same as we said before, which is that the electric field strength goes like 1 over the square of the distance, directed radially outward. So the electric field vector then would point away from that, and the strength of the electric field goes like 1 over the square of the distance our script being the vector between r and r prime. Okay? And so now you're just going to play with that. There's some exercises just to get you used to doing this. Just very explicit. And then we're going to do a couple of instances where we take two different charges and practice the principle of superposition. So you have a couple of different charges that are present, Q1 and Q2, at two different locations. Call it R1 prime and R2 prime. Then the electric field over here is simply a superposition of the electric fields caused by both of these charged bodies here. And so the calculation then proceeds as you would expect. So the net electric field is the vector sum of those two. Okay. Okay. So now let's consider a dipole, which is an interesting example of superposition, and one that we will encounter several times as we go through this. We have a plus Q and a minus Q. So when I write plus Q and minus Q like that, you could make the drawing assuming that Q is a positive, and so the negative Q is the negative. Distance A and A around, oriented along the y-axis, right? And then I wanted you to calculate the electric field on the midline between these two. The dipole field is, of course, generally what you would get if you do it for any point, and it's a little complicated in the far field, but we'll consider that as we come to it later. But for now, I just wanted you to get a feel for the superposition. So the two electric fields here, there's going to be one that points away and the other one points towards, and then they should have the same magnitude, right? Because they're both the same distance from that point. So the net electric field is downward. And so we have here then that E1 is using the general expression, excuse me, that's not what I meant to write. The general expression for the electric field okay, does everybody see why the A comes in with the negative there? That this is the first charge up here, and its location is at A y hat, and you subtract that. Okay, and then the second electric field then, opposite charge in the other location there, the opposite along the y-axis. Okay, and then the total electric field then is obtained by summing these two, which you get minus 2qa over x squared plus a squared to the 3/2 along the y-axis. Okay, that's no approximation involved. That's true for any value of x. And in fact, suppose we take x equals to 0. That's kind of an interesting case. If x equals to 0, the electric field is in minus 2qa over a cubed y hat, or in other words, minus 2q over a squared y hat. Can you see why that ought to be the case? If you go up here and you're looking at, say, a point right here on the origin right there. I want to know what the electric field is. Well, the electric field, there are two contributions, one from each charged body. They're in the same direction. One is repulsive, one is attractive. That is the one point. They both point downward, I should say. Okay, and they're both going like 1 over the square of the distance. Okay, so you just get two electric fields like that. Okay, but the far field is the one that I wanted you to look at in the homework. Let's suppose that x is very far away, much larger than a. Then the approximation that the denominator can be approximated by x cubed. So then the electric field is going to be minus 2qa over x cubed in the y-hat direction. Mr. Luker.
The one you just finished, was that letter E that you were working
Yeah, I'm working on E now.
Oh, now you're working on E?
Yeah.
Okay.
I started
I was a little bit confused.
I'm sorry.
Like when you started simplifying.
I'm sorry. This is the dipole. I figured. Okay. Do you have any questions about D? It's pretty straightforward.
Yeah, no, I'm good with D.
Okay. So I jumped to the dipole. Okay, so notice that the dipole field strength, the monopole field strength, which is a single charged body, falls off like 1 over the square of the distance. The dipole, which has two bodies with equal charge opposite, goes like 1 over the cube of the distance, because you have a partial cancellation of their field. And you could continue this. Suppose we have two dipoles, and we put them side by side, but suppose that the two dipoles are themselves oriented in opposite directions, like this. So we have a square arrangement with charges that are arranged in that fashion. So it's like two dipoles that are opposite, opposing. So the dipole fields cancel. So how do you suppose that the field strength, the electric field strength then, this is called a quadrupole, and you would not be wrong to think that the quadrupole field strength is going to go over like 1 over the 4th power of the distance, because you get a cancellation of dipole fields. Okay? How would we create the next one, extending this pattern? You want to cancel the quadrupole field by putting in another quadrupole. How would you arrange it opposite quadrupole?
Yeah, like the planes would be perpendicular or parallel to each other?
Yeah, you want them shifted perpendicular in the plane here, so take another quadrupole and shift it perpendicular to that, but you want to opposite, you want to switch the charges. So in other words, a cube with a quadrupole plus, minus on the top, and then the opposite, minus, plus, minus, and then plus here. That's an octupole. Octupole. The electric field strength will go like 1 over the 5th. It gets weaker and weaker and weaker. You have these partial cancellations going on, and each time it starts getting weaker. So that's kind of interesting. We're not going to do that. You could do this in your, if you want, for a little extra challenge. Turn it in for extra credit. Work out the quadrupole and octupole fields far field, right? Okay, the other one, number F, has to do with not exactly a dipole. It wouldn't really call it a dipole, because the dipole usually consists of opposite charges. But what happens if we put these two charges having the same sign? Look at the far field solution, and in that case, you get that the electric field, because they have the same sign, is along the x direction. Not surprisingly, it should be pointing away. X squared plus a squared. And then if we approximate that in the far field, we say that that denominator can be approximated by x cubed. We neglect the a there. Then the electric field goes like 2q over x squared in the x direction, which is back to our monopole field, right? Having a total charge of 2q and a distance x from that. So the separation of those two charges is negligible, so you can treat it in the far field like a monopole. Okay, does that make sense? The last one is that tetrahedron of charges, plus, and then on a negative like that. I wanted you to examine the electric field in the center, right in the middle of that tetrahedron, and it points from the positive charges towards the negative charges. That is, if you consider one line, one edge of the tetrahedron connects the two positive charges, and another edge connects the two negative charges. And looking at it in that fashion, the electric field will point from one edge, that positive edge, to the negative edge. And the coordinate system I've chosen, that's the x-axis. I haven't drawn it quite that way, but the electric field then. And this is simply an exercise in using a Cartesian form to carry out this principle of superposition. Makes it easy using it in calculations. Okay. So it shows you both an exercise in the Coulomb's law expressed in Cartesian form, and the principle of superposition, and using the components to calculate things. Any questions about that? Okay. So now for Monday, we're going to consider the potential energy of two charges, and please read the text to discuss this. Of course, the potential energy we have a force associated between the two charges and a potential energy. So the force, Coulomb's law, goes like Q1, Q2 over the distance squared, using R as the vector from 1 to 2. Or you could also, if you're wanting to calculate things, it may be easier to use the R vector over R cubed. And the force goes like 1 over the square of the distance between the two. Now, of course, there's a potential energy associated with this force. It's a conservative force, and the potential energy goes like Q1, Q2 over R. And so this encapsulates all of the different possibilities that we could have. The two charges being of the same kind would be a repulsive force, and then the potential energy is positive, which means that you're uphill with respect to the point at infinity, separating the two charges from infinity. If the two charges are opposite, the force is attractive, the potential energy is negative. That would be like being downhill from the point at infinity. So let's consider the case where the two charges are the same. Q1 and Q2 are the same type. That is, they represent positive or negative, as we call them, and they're the same type of charge. And then the potential energy will look like this as a function of R. Go like 1 over the distance. Right? And so the rule of thumb is that the force is going to be directed in the direction of decreasing potential. Right? The force is the negative gradient of the potential. So whatever direction decreases the potential in its most strongly, so that would be radially outward, and as a function of radius, it looks like that. Okay, so if a body starts off at rest at this position, or the two bodies start off at rest with that separation, there's going to be a repulsive force. The potential energy is going to go down as they move away from each other. Whereas if Q1 and Q2 are opposite, the different types, then the potential energy is negative, which means that to go downhill, you're going to pull them together. It's an attractive force. It's going to pull them together. So this way of combining all of those possibilities is a very convenient way. You just take the product of the two charges. You don't have to worry anymore. You don't have to keep in mind anymore, am I dealing with, I've got two different types of charge and so forth. It keeps it all there. It's a very convenient, compact way of accounting for all the possibilities. Okay, now just as we said that the electric field superimpose, the forces superimpose, potentials just add. So if I have three bodies, 1, 2, 3, then the total potential energy is going to be the sum of the potential energies associated with each of the three pairs. There are going to be three terms involving the charges, the three charges, and the distances between all three. Now the last, let's see, you have a homework which involves that tetrahedron again. Tetrahedron of four charges. Q1, Q2, I think they're all, there's plus Q, minus Q, minus Q. And you are to find the total potential energy associated with that. How many pairs are there? Have four charges, how many pairs? No, six pairs. How many edges are there of it on a tetrahedron? There's 6. You can see I drew all 6 of them there. So there's six edges. So every edge represents a pair. So there's 6 terms involved in this. And what is the significance of that? That total potential energy, what does it mean? So I have here all 6 terms. 2, 3, V, 2, 4, plus V, 3, 4, 6 terms. Potential energy associated with each one. What does that mean, that total? How about let's go back, remind ourselves what it means in that first case, just a single pair. What does that potential energy represent? The amount of kinetic energy it could have in the case with reference to infinity. So it would mean, for example, in the case where they're repulsive, if I start off at that distance and let go of them, then they'll fly apart And asymptotically, the system will have the kinetic energy, that much kinetic energy. Right? Other way around, if I start at infinity and it's attractive, and I let go and they pull together, then the kinetic energy will be equal and opposite to the potential energy they have at that point. Okay? Because the total energy start off at 0. So that's another way of looking at it. Related to the work, it's the opposite of the work done by the electrostatic force, by the force, the electric field, against each other. So if it's repulsive, I have to pull them in together, right? So I'm doing negative work, working against the electric field. The electric field is doing negative work, and the potential is the negative of that. Okay, so that, going back to this case then, how about that? That would represent, if I start off with this, if that potential energy is positive, it means if I let go of the thing, it'll fly apart. If I let them fly apart to infinity, yeah, okay, but some of these are attracted and stuff, so it's a little more complicated than that. So how about if I start off at infinity and pull them in together, the potential energy is the negative of the total work done by the electric field. So that's what that represents. Any questions about that? Just a matter of calculating. Calculationally, it should be pretty simple. Just, again, illustrating how to calculate things, and the principle of superposition, obviously involved in this. Okay, now we're getting into now the next subject in the text has to do again with the mathematical development here related to this, and we're examining in particular the first property of physical things. And what is the first property of physical things? No, that's the first principle. What's the first property of physical things? Quantity. Quantity. That's, of course, what math studies in particular is quantity. Okay, so what we're going to study is having a physical body, for example, this. In this case, it's kind of hard to rearrange the parts of it, the needs. I can do some rearrangement. Okay, that's not too bad. The fluid that's in there, I could rearrange it if I open the thing up, let it leak out. The fluid is rearranging its volume. And in fact, let's consider now a fluid is a really nice example of this, especially an incompressible fluid. And you're familiar with an incompressible fluid, almost incompressible fluid, and that is water. Here we are making another abstraction. We're going to consider an incompressible fluid, and you have a familiarity with a fluid that's almost incompressible. So this is a pretty easy thing for you to imagine. Fluid that doesn't change volume. It simply rearranges the volume that it has into a different shape. Okay, so it flows, and we want to study that flow. And in fact, I could think of it in one way by talking about the mass of the water. Of course, the parts themselves can be thought of virtually as having mass. Each of the pieces has mass, and I'm rearranging the mass. But really what I want to focus on, I'm going to use that mass, which is a quality, as a kind of substitute. What I really want to focus on is the volume. I want to take the volume and rearrange it. So I could take a sphere and distort it and have the fluid flow and make some other shape, like an ellipsoid or some long cylinder or a cube. And so I'm going to study that. That's what we're going to be doing with the vector calculus, is studying that kind of flow. We're focusing on volume primarily, and then we're going to extend that to qualities, other things that could happen, like mass flow, charge flow. Those are qualities of the body, but we're going to start off, again, because math focuses on quantity, we're going to start off with quantity. And now, but he does this in order to kind of help your understanding of it. He'll substitute sometimes mass for the thing that's flowing, and we look at the mass. But really what we're studying ultimately in the mathematical is the extension, and rearranging the extension, the body itself. Okay. So let's consider then that we have, here's an example of what I'm talking about here. Okay. this is going to represent the flow of something. And it's going to be a vector field. And I have various different pieces of this, and let's examine these pieces. So the first here is the velocity. If I have some liquid body, and I have some piece of it over here is moving in this direction. Then I have to be rearranging it, and some other parts are going to have to move as well in order to keep up with this. Okay, so these parts themselves have, at each piece I can associate with it some kind of a velocity, which tells me how fast that piece is moving and in what direction it's moving. Okay. Now I also want to consider, if I'm talking about mass flow, I want to talk about how much mass is in that region. So, and the way I do that is by having a little volume here. Take a little piece of it. And I want to know, inside of that volume, I'm going to call that volume dV. This is a volume. It's an infinitesimal volume. It's just a little piece. What is the dimensionality of dV? Any volume, yeah. It's the length cubed. It's just a small volume, but it's a volume. Tiny little volume. And I put the d in front of it because what I mean in that case is it's really small, arbitrarily small. I don't want it so small that I may start encountering the pieces of the water. I mean, you can get down really small and then you start encountering some pieces of the water on the molecular level. I don't mean it that small. What I mean, we're considering instead this is a continuous fluid, right? And we're abstracting this. It's a continuous fluid, and we just mean some volume associated with that continuous fluid. It's very small, much smaller than the size of the droplet or anything else. Okay. And now how much mass is in that little volume? Okay, well there's going to be a very small amount of mass. A very small measure of the mass. If I measure the volume, the mass inside of that volume, that's a little m there. If I measured the mass contained in that, again, remember the mass, primary definition of mass is resistance to the impetus. But I'd have a small amount there, and the proportion between them is called the density. This is mass density, rho m. And what is the dimensionality of the mass density, which you can get from that relation that I just had there?
Length to the -2.
Yeah, mass per volume, right? Mass per volume. A mass density is a mass per volume. Okay, so this current density is a vector that describes how much mass is flowing. It's a combination of, and what is the rate of mass flow? How much mass is flowing associated with that little volume. You have the velocity of it and the measure of the mass, so it's a rate of mass flow. And let's look at, and remember it's the mass density times the velocity. Okay, so let's look at the dimensionality of this current, mass current density. So it's a mass per length cubed, and what is the dimensionality of the velocity? Length per time. So it's a mass per area per time. How much flows across a given area in a given time? Little area, little time. So rate of mass per area per time. Okay, so now let's suppose we have this flow that's going on. Okay, before I jump to that, we could, remember we said we're substituting in this to make it a little easier to understand. What we're really focusing on is the volume, though. So not the mass, but the volume. So we could transpose this and say, really, and it's kind of convenient, that a cubic centimeter of water, if I have a little droplet that it has a volume of a cubic centimeter, it will have about 1 gram. of mass. The mass of that cubic centimeter will be about 1 gram. In these units, it makes it kind of convenient just to swap back and forth from volume to mass. But really what we're wanting to focus on is the volume flow, and which you can do if you have an incompressible fluid. You can think of it that way, just looking at the volume flow. Okay, and so rho would be just 1. It's how much volume is there per volume. So it's when this droplet is moving like that and extending itself. I don't want to do that. When it's extending itself like that, it's reshaping its volume and it's moving out into the environment. And in order to do that, of course, it's having to change its move in from the environment, move away from the environment somewhere else. Moving out into the environment, it's just extending its volume in that direction and moving volume from somewhere else. Okay? So we could also talk about just J of the volume itself, which is just the velocity. Okay? So in that case, how fast is the volume moving? And so in that case, J is going to be a volume per volume. It's a volume per volume times a velocity. So it's just a velocity. Okay. You're just transporting some volume to another volume, relocating it. Okay. Okay. Because mathematics is focused on the quantity, and we're using the mass as a kind of a placeholder here for quantity in this discussion. Okay. It's a placeholder for the volume. Okay, now let's suppose we have then a fluid which is flowing here, and I have some, let me read, I want to, well, no, that's good to begin with. I suppose I have an area like this, dA, and I have a current density flowing through that area, across that area. What is the total amount of mass or volume that flows across this little area? Okay. Well, it will be just J times the area. Remember, we said J is the rate per area per volume, so we multiply by the area. Now we just get a rate of flow. If it's mass flow, it's a mass per time, right? So let's do a mass flow. Mass flow is a mass per area per time, so this is a mass per time. It's a rate of mass flowing through that little area. Okay, but now suppose that that area is not, I drew that area to be right perpendicular to the flow. But what if the area were inclined? What if I had a little area vector like that that's inclined off of the flow like that, and the flow is in this direction? It doesn't seem like you're going to get as much flowing through that little area because it's not oriented in such a way as to give maximum flow. In fact, you could have it so you're not actually getting any flow through this little loop because if the flow is parallel to that, it's in the plane. So we're going to describe this area vector, this area by a vector. And we've done this before. What is the area vector associated with that? The magnitude and direction. So this is a vector, dA. What would you think would be the magnitude and direction of this vector? Could be a cross product of the legs, right? In that case, the direction would be related to the plate, the little tile, perpendicular. Now we have two choices, so we're picking one choice of this direction. You have to keep that in mind, and there's going to be a reason for picking that choice as we come to this later. We'll have a way of designating, of choosing one direction over another one. But for now, we just say we have one of those chosen. So there's a perpendicular, one of the perpendiculars. So the perpendicular to the tile, to the area. And the magnitude is just the size of the area. So that's the vector. Okay, so now how do I describe the flow through that in terms of these vectors, J and dA? how much am I going to get? Is there some way of describing that in terms of these vectors?
Is it a dot product?
Yeah, it's going to be a dot product. And you see that that would be J dot dA. Now gives you the flow through that area. It's the rate through, rate of flow through the area. If the area is perpendicular to J, you're going to get nothing flowing through that little loop. If the loop is oriented parallel to J, then you're going to get maximum flow. But notice if the area is in the opposite direction, we get a negative flow. Okay, so you can see what we're doing there. The direction we associate with this. Whoa. Okay, thank you. Yeah, I've got them all over the place. Sorry. Yeah. How do I stop? Stop. Thank you. Okay. A there is choosing a direction, right? There's a positive flow and a negative flow. Because if A, dA is parallel to J, then I get positive flow. If I flip this little tile over in the opposite direction, I get negative flow. The dot product gives me a negative. So what could that mean? Well, you're trying to keep track of the direction of the flow, not just the magnitude. And you've assigned a direction associated with this tile. I want to know what's flowing through this way. And so if I get negative flow, I'm actually indicating that it's going in the opposite direction to that. So I could do, for example, let's have a flow. How about a flow coming out of a faucet? And I have the liquid flowing down like this. And J is the vector fields associated with the rate flow associated with this fluid here. It's zero outside, it's not zero inside. I'm going to take a little wire loop, maybe not a wire, maybe just an imaginary loop, and I want to know how much is flowing through this, but I have a direction here associated with it. Is it flowing this way or this way, right? So my little, depending on how I choose that, I'm going to get positive or negative flow. Okay, now this is going, I'll give you a little preview here. Let's go back to the electric field. That's coming out of a positive charge like that. What if we were to put a surface surrounding, a sphere surrounding that, and look at as though the electric field were like a fluid flow coming out? Then I could account for a little area here, and I want the electric field that's parallel to that area. Whereas if I had a and then I would add it all up over the whole surface, I would get a net flow outward. Whereas if I had a negative charge, the electric field vectors would be inward. Then if I still have the area vectors pointing outward, but now the flow is like it's inward, it's coming in. So that gives you a sense here, the reason that we might choose an area element to point outward from the volume it's bounding. Okay, so that's generally what we're going to do. These area elements are going to be part of a complete surface that surrounds some charge. And we're going to point the area elements outward. And then we can account for flow out or into the volume. That's why we would choose the area element to have a direction associated with it. Okay? So and that would be the same thing. If, for example, you had, suppose you had in your bathtub, you've got the sink, the drain is open. Come on, I can keep extending this, can't I? Indefinitely? No? All right, I'm going to add to this. All right, so I have, let's suppose I have a drain here, and the fluid is flowing into the drain. And then I'd have little area elements pointing outward. I could tell, in fact, that I have a net flow inward because the flow over the whole circle is negative. Or suppose I have some way of pouring water, so I could, on a surface like this, I could have water draining down onto here. I would have flow outward from that spot where I'm pouring water onto the surface, and the water would flow outward like this. And by choosing these area elements to be in that direction, I could tell, in fact, that I have a source of water somewhere here, and it's flowing outward here and flowing inward over there. Okay? So that's the reason why we have this choice of the direction on the area element, aside just from giving the relative orientation of the area to the current flow, we can actually tell whether it's flowing in or out of a volume. And that's going to be very helpful for us. Okay, any questions? Okay, no office hours this Friday, of course, and I'll see you on Monday. Be sure to turn in your homework, please. Oh, yeah, it does. Yeah, you can put your homework there on the